Now, these, as I mentioned that in the case of Van-de-Graaff accelerators, the ions were produced inside the terminal where the power to produce these ions was coming from the motion of the pulley, high voltage pulley, and that is moving, that is rotating at a fixed speed, therefore power was limited. And as a consequence of that, roughly in all the Van-de-Graaff accelerators, only protons and He plus ions could be produced. Now, any experiments or any research should not be restricted to only protons and He plus. Even heavy ions should be accelerated and they should be available for it. And therefore, how it could be done? And it was done. A new kind of accelerator was built, and there, instead of just having this accelerating column, you add one more column, so two columns. One is, this is column and another is column. So that means with the same high voltage, you can get 2 times. In the case of singly negative ions, you can get 2 times energy. But as I mentioned that if the charge state could be larger, then even the energy could be higher. So here it is. Now the problem which will come here is that this is a positive potential, and therefore if you want to use this, then it has to be Coulomb attraction. It can be accelerated only, for example, this is, let's say this is first column, this is second column. And if the ions have to be accelerated to ground potential or some energy to this, then this cannot be accelerated unless the polarity is also reversed. So in the case of tandem accelerators, the particles are injected as negative ions instead of positive ions. So you can see that the particles, this is the ion source, and then ion source, the ions are analyzed for a particular mass and charge here, and then they are injected into the first column section, this one, and till that time they are negative. And this is, they are attracted by Coulomb potential by this, this high voltage terminal, and they are accelerated to this. Now you see, here it was Coulomb attraction, so that is why they were accelerated from this potential to this potential. Now if it remains negative ions, they will not go out because they will be attracted further by this high voltage terminal, which is a positive potential. So therefore, inside this high voltage terminal, the polarity has to be changed. And that is what is done. In this case, inside the high voltage terminal, a unit called stripper unit is installed, and a stripper unit could be either carbon foils or it could be some gas, mainly inert gas. And when the beam passes through that, then there is an interaction, there is collisions, and these negative ions lose a lot of electrons. It could be one loss, one electron loss, or it could be many. For example, in the case of let's say oxygen, even all the electrons are stripped, and then it will be 8 plus. And of course, how many electrons will be lost will depend upon with what energy these ions, negative ions, are coming. So it depends upon, and that will depend on the voltage on the high voltage terminal. So at high energies or high voltages, many more electrons can be removed, and much higher charge state ions can be produced, and then they are positive ions, and therefore they will be repelled by this high voltage, and repelling will be, the energy will be charge state times V, and therefore in the second column section or second accelerator, so second accelerators, much higher energy can be achieved, and that is the advantage in the case of tandem accelerators, that you can get much higher energies. Secondly, heavy ions beams you can get. Thirdly, that because the ion source is sitting at the ground potential, not in the terminal, and therefore you can give any amount of power to the ion source to create negative ions of anything. So in fact, the negative ions of right from proton to uranium, they have been produced, they have been accelerated, and there is no problem. So this is the tandem accelerator. But tandem accelerator is still for charging the voltage on the terminal, raising the voltage, is still the belt charge was used in the case of tandem accelerator. And in the case of belt, what happens that you know that comb is there, and comb will have sharp surface. As a consequence of there will be sputtering of the belt, and some lints will also form. As a consequence of that, there will be a electric field will not be uniform across the belt, and that will give a problem, and that can increase the uncertainty in the voltage, because the charge transfer will not be uniform. And this problem was solved in the case of Pelletron, which I will be discussing little later. So in the case of tandem accelerator, basically you can see the energy here is E in, that means the energy of the ion which is coming out of the ion source, let's say it is E in, and when it enters in the first column section, it is singly negative ions, so it is 1 times the EV. And in the second electron, suppose the charge state is in the second column section, because the charge state formed here in the stripper system is N plus, therefore it will be additional N into EV, and therefore the total energy becomes N plus 1 times E, and that could be much higher. Now from the ion source here, normally the voltage is used to extract the ions are in the range of 30 to 100 keV, and therefore now suppose you take let's say oxygen. I am just as an example oxygen, and let's say this E in is very small, 30 keV as compared to several million volts. So I neglect it. So its energy becomes N plus 1 into E. This meant M. Now oxygen, if you take, had it been Van-de-Graaff, then it could have been only singly plus. So the energy, let's say in the case of 10 MeV, the energy could have been only 10 MeV. While in the case of tandem accelerator or oxygen, all the 8 electrons can be removed at 10 MeV, 10 to 12 MeV, and then the energy will be 8 plus 1, 1 times in the first one, and 8 times in the second one. So it will be 9 times the 10. So it becomes 90 MeV. So you can see what was only 10 MeV in the case of Van-de-Graaff. Now you will be able to get 90 MeV oxygen 8 plus beam. So a lot of new experiments can be done with this. And of course, after that, you analyze it for the energy, and then you correct it also. If there is too much fluctuation, you can give a feedback, and then you can stabilize the voltage. After that, this is a switching magnet where the beam could be thrown into the analyzed beam, can be deflected into various beam lines where experiments can be done. So this is tandem. Now as I mentioned that in the case of tandem, kinetic energies can be much higher, and it uses two column sections. And you can see here, this for the sake of demonstration, we are seeing that we built one 2 MBB tandem accelerator here completely indigenously, and you can see that this is first column section. You can see that this is first column section. You can see here both the column section. So ions coming from this side, they are accelerated, negative ions. They are accelerated up to this place to 2 million volts. Then they are converted into positive ions and they are further accelerated. And this is the pressure vessel. The whole thing is put inside this at about 230 psi so that the high voltages could be obtained. Now, depending upon how accurately you form the accelerating tube is nothing but a set of electrodes plus the insulating gaps in between, and that is built here. You can see. So these accelerating tubes have become a specialized atom, and depending upon how accurately you form this, the voltage gradients could be much higher as compared to the ones which were used earlier. And so you can see this accelerating tube is one of the most critical component in the accelerator, whether it is a Van-de-Graaff or any other accelerator. And one thing is that there has to be ultra high vacuum inside this, and that will be decided by what kind of joining is there and what kind of insulators are used between electrodes and what kind of material is used for joining. So that will decide the what kind of vacuum system you can achieve, because there the degassing will take place, and you can so this is a special item, and performance of the accelerator will also depend how accurately and how nicely you can make the. In order to avoid the electron scattering, different kind of electrodes are separately put, and they will not allow this electrons to hit the insulators, and therefore the life of the accelerating tube will be normally in present day accelerators, a gradient of or the gradient of about 1 million volts per meter in this at room temperature are easily available, and they can be obtained. So these tubes are constructed of insulating material. Commonly they are ceramic because the degassing is much less, or the glass with vacuum tight seals to metal plate electrodes. Vacuum seals are extremely critical in view of the high external gas pressures of up to even tube. See, this accelerating tube is installed inside the column section. Now inside is vacuum, many times 10 power minus 9 to 10 power minus 10 torr, but outside is a pressure, because you need insulation from outside also. So you can see that both the concepts are used. Inside it is a high vacuum, outside it is a high pressure, and this sealing of the accelerating tube has to stand both high vacuum and high pressure. The electrodes are connected to equipotential rings in the voltage generator columns to maintain the uniform potential distribution. Because for focusing the beam, it is very important to have accurate beam this voltage distribution. Not only you have to worry about fields or the voltages, but also you have to see that the electrodes or the entire accelerating tube components, they are not subjected to high particle radiation, and that has to be taken care of. And one of the things which you have to take care of is that the electron suppression has to be there, so that these electrons don't hit the insulators. and therefore one should minimize the secondary electron emission by applying the selected materials. So these are some of the things which you have to take care. Now, as I mentioned that in the case of tandem accelerators, we were using the belt for charging, and belt has difficulties. For example, charge transfer may not be uniform, and therefore in order to improve that, another modification was done, and the accelerator which is where this modification was applied is called Pelletron accelerator. So in this case, Pelletron accelerator, what is done is that this belt is replaced by a pellet chain, and this pellet chain is made of metal pellets coupled with the insulators. And this Pelletron charging chain, which is advantageous over the tandem accelerator, was developed by Herb and his collaborators in National Electrostatic Corporation in USA in 1960s or so. And this is has improved the charging efficiency and voltage stability considerably over older Van-de-Graaff or even the tandem accelerator. And therefore in Pelletron accelerators, you can get much better stability voltage wise and hence the energy as compared to the tandem. The belt suffered from the number of operational difficulties, including terminal voltage instability and susceptibility to spark. As I said that because of that high voltage corona needles or mesh, sharp surfaces were formed on the belt, and therefore those belts were subjected to sparkings. And those things are avoided in the case of Pelletron, because pellets which carry the charge, they are conductors, and therefore charge will be uniform and there will not be any spark. There is no voltage gradient or there is no electric field over there. So all the pellets will have roughly similar charge. And the chain is more durable because there are no sparking, so they are durable than the belts, and they don't produce any sparkings. As a consequence of that, terminal voltage stability is much better. It eliminated the belt dust. So this was one more serious problem in the case of Van-de-Graaff as well as tandem accelerators, that because of those sparkings on the belt, there was dust formed, and those dust will pick up the charge, and they themselves become, say, source of high voltages, local high voltages. And so dust problem is solved in the case of Pelletron. Chain doesn't limit ultimate terminal potential, and it is in use in electrostatic accelerators up to about 30 million volts. Here, their operational accelerator has been built with 30 million volts in France, Strasbourg, and that is routinely operates at 25 million volts. You can see that in India also we have two Pelletron accelerators. One is 14 UD Pelletron at 14 UD Pelletron at TIFR, Tata Institute of Fundamental Research, Mumbai, and that is in operational for more than 20 years now. A similar kind of accelerator with the 15 UD. UD is that their nickname. These are both supplied by NEC, National Electrostatic Corporation, and 14 UD is able to go to 16 million volts. This is at IUAC, Inter-University Accelerator Center, and New Delhi. And the line diagram of this is shown here. The negative ions from the ion source are mass analyzed and they are injected into the first column section. They are accelerated up to the high voltage terminal where the negative ions are converted into positive ions, and then they are further accelerated, and then there are of course the several beam lines where the experiments are done. These pellet chains, which is the biggest improvement of pelletron over tandem, they are made up of metal pellets connected by insulating nylon links. And metal pellets or the plates are charged using the effect of inference in the electric field. That is called induction charging. See, this is not, you are not putting any surface, sharp surface there. They are done by induction charging. And that is the biggest advantage here. And there is a much more accurate, much more efficient way of transferring the charge, charging the system. For positive charging, the electric field between the negatively biased inductor electrode and the pulley pushes electrons off the pellet while they are in contact with the ground. Since the pellets are still inside the electric field as they leave the pulley, they retain the net charge, positive charge, and that charge is transferred in the similar way into the terminal. So this, as there is another advantage in the case of pelletrons, that while the pellet chain is moving up, it carries positive ion. While in making a special arrangement in the terminal, you can also transfer the negative charge to the pellet chain, and that is possible, and therefore this pellet chain is able to transfer the double charge 2 times. You can see here that pellet chains are made of pellets. You can see here. You can see here these are pellets and they are connected by this. And point to note is that there is a electrode here, and that induces the charge onto these pellets, and that is transferred to this. And there is no sharp surface, there is no sharp comb or anything involved. It is by induction. So that is a much better way of doing it. Now it is going up here, so it is charging here. Now then there is a pickup pulley here. And that pickup pulley, see here the voltage applied was minus 50 kV, for example. So when the negative voltage is applied, it transfers the charge, it induces the charge, which is positive, onto the pellets. Here that positive, some part of this charge is picked up by this, and then there is a electrode here, which becomes positive, and so it just takes reverse of that here, and this remaining charge, which is almost very small charge, is picked up here. So most of the charge is going there, and that charge is by similar system is transferred to this, which is connected to the high voltage terminal. While returning this pellet chain, this is positively charged, so by induction a negative charge will be generated, and then the suppressor electrode is also put here so that there is no spark. So you see the positive charge is going here, negative charge is coming here, so it gets 2 times voltage on or charge here on this one. So that is the advantage, and since there is no sparking, and so the voltage stability can be much better in the case of pelletron accelerators. So most of the present day accelerators are pelletron type, and they are able to give much better stability, beam stability, and more accurate experiments can be done. You can see that There are several advantages of Pelletron over that, so I'll just I've listed here. The typical charging currents are in the order of 100 to 300 microampere. Very small charging current is required. High voltages up to 30 million volts have been achieved, have been reached. And that accelerator starts work in France is routinely available for 25 to 30 million volts. The terminal voltage can be regulated and controlled by varying the charging voltage between the inductor and the suppressor, electrodes and pulleys. Charging voltage in the range of 50 to 100 kV is required. The charging chain for the high voltage generation exhibit good voltage stability. That is the biggest advantage. For example, at 14 million volts, a few kV, 1 to 2 kV can be achieved. For example, at Mumbai Pelletron, it's a 14 million volts, and the voltage stability or energy stability of about 1 to 2 kV could be achieved. Similar energy stability at 16 million volts of Delhi Pelletron. So they are highly reliable, and since there is no sparking or anything, their life also becomes bigger, much larger as compared to the. Thank you. Thank you very much.